This is a image processing project I worked on in MATLAB. This one specifically deals with image downsizing and resizing, as well as filtering and uh, image image interpolation. I had another one with quantizing for images and another one with audio processing as well. And overall, yeah, and here I have it. So part one was, yeah, mainly just going through images and downsizing and resizing by a certain ratio, and then also using some filtering, whether that be low pass, high pass, or Laplacian filtering. And part B consisted of some Fourier transforms on the images as well as some Gaussian filtering. Now, this project was, um, it definitely had an interesting aspect where it taught me to kind of think differently with regards to certain problems. So, with respect to images, um, it's easy to think about images in sort of this natural human way we evolved to, which is just trying to look at something and gain information from it. But when you have digital images, you really, to solve certain engineering problems involved in them, you really have to think about an image as a digital, a collection of, or sorry, a matrix of pixels or a matrix of binary values. And that makes it a lot more useful to think about how interpolation works, essentially. And I'll just go through and briefly explain each one of these parts. So, first part here, you'd see it's just going through, and a lot of times it's difficult to tell the changes that are happening from our human eyes. Um, but it's going through and it's shrinking images and it's trying to resize them, and it's using the nearest neighbor, bilinear, and bicubic interpolation methods. Now, of course, the bicubic is the most computationally intensive, and of course, linear, or sorry, nearest is the least. But for how computationally hungry it is, the bicubic is certainly going to look a lot better to human eyes. So depending on what you're doing, if you're trying to stream video or if it's just an image, you really have to look at how much processing power you can afford, um, depending on, yeah, what your goal is there. Um, but yeah, if we just look at this with our human eyes, we can clearly see the bicubic interpolation is just miles ahead of the nearest, significantly better. And well, with regards to those specifically, nearest interpolation is essentially looking at the pixels around itself, and it's trying to use that information. And then as it goes from bilinear to bicubic, it's using a larger matrix. So bilinear is a 2 by 2 matrix, and bicubic is a 4 by 4 matrix. And so yeah, it's gonna get exponentially more computationally intensive for those tasks. So yeah, that's basically all this code is doing. We have this variable here. This is essentially going to be the exponent of um, essentially when the image is being decreased by any sort of factor. That fraction is going to be 1 over 2 to the power of this variable. And then that's going to go through several times, 1 for 1/2, 1 for 1/4, 1 for 1/8, and that's why we have so many loops here. Um, yeah. Secondly, for these image filtering section, we're using low pass, high pass, Laplacian um, to create different effects on the images. And this part wasn't necessarily the most intuitive for me. With signal processing, it's easier to think about when you just have some sort of high frequency AC signal or some low frequency AC signal, of course, the low pass is going to allow the low frequency signals and the high pass is going to allow the high frequency signals. But when you think about it in terms of an image, you have to kind of change, you have to kind of think about it a little differently, and it seems a little strange at first. Because within the context of an image, you have to think, okay, what does low frequency mean in terms of this binary matrix, this matrix of pixels, right? And so, of course, you could tell by observing it what's happening, but the high frequency filter is going to allow for high frequency to pass, but in an image's case, what it constitutes high frequency is large pixel value changes between neighbors. And essentially, if you have a matrix of pixels, right? Or we just do two. So say this value is, 0, 0. Say we just have two bits to work with here, and this is 1, 1. This is the maximum difference possible between these two values. So that's a very, very high frequency because there's so much change going on, right? But say this neighbor was just 0, 1. Well, that's not a huge difference. So this is going to be a lower frequency on the image. And when we look at the image, what that means is the high frequency filter is going to essentially highlight the edges of an image. And the low frequency is going to create a blurring effect. Now, those are both the human way of looking at it, because ultimately, yes, it is useful to think about it as a computer thinks about it, but for a lot of use cases, the output of the image, you want it to be useful for human consumption. And of course, uh, these are lossy algorithms that you're performing. And that's okay sometimes, depending on the use case. If this is like streaming video for entertainment purposes, yeah, you don't necessarily need to preserve every single pixel value. You just need to keep an image that a human can understand and is still high enough quality for what the user expects. So yeah, you could see, and here with this grainy image, um, that graininess is basically a bunch of high frequency points across the image. So when you pass a high pass filter through that, like you see here and here, it's going to almost make it worse in a sense because it's just highlighting all that grainy effect, um, which just makes it look worse from a human's point of view. And the low pass will help the green effect from a human's point of view because it'll smooth out those large differences.